Hi, welcome guys. So this video, we will talk about rank and the duality theorem in the linear algebra. So basically, I create a list talking about all the linear algebra proof. Basically, most of them I think is very important. So I will try to predict. I'll try to do take a list, right, to press proof all the theorem. I think which is a non-trivial theorem in the linear algebra. Okay, so hope you guys subscribe, and I will post this video link below. Yeah, so if you want to see more. And in this video, let's talking about a very important theorem in the linear algebra called the rank nullity theorem, and we will give the proof and talking about all the details. Okay, so basically all my setting is that V is a finite dimensional vector space. So yeah, so V is a finite dimensional. Usually people working about a complex n or a real number n. Okay. Yeah. So so the result is basically dimension V. So V is finite dimensional equals to so-called if you have a linear transformation from to vector space V to W, and become a dimension kernel T plus dimension of image T. Okay, and what I want to say is that let's see, yeah, hopefully hopefully let me change the color. Yeah, I just think this color is not good. Okay, so two factors that's defined the notation. So kernel T means that all the vector belongs to V such that TV is 0, right? So so-called kernel, and the image of T, which is trivial, just TV, right? TV for all V belongs to V, right? So you take, yeah, and the fact is that easy to prove. I will not prove here because trivial image T and kernel T and image T are both subspace. Okay, so easy to prove by axiom. Okay, so that means that the kernel T can be viewed as a subspace of V, and this image of T can be viewed as. Okay, so we want to prove this. Okay, so the short proof is that you know more about advanced mathematics, so you can use group isomorphism theorem. Sorry, group homomorphism theorem. So let me just quickly. Okay, if you don't know that, I have a video proof. So basically, the group homomorphism theorem says that if you have a group homomorphism from G to H, then G is isomorphic to other G modulo kernel rho is isomorphic to image rho. Okay, so this is the group homomorphism theorem. If you notice, then easy to show that you just apply on V to W, and now your group addition is just a vector space addition, so easy to show. So you from this, right, you know that V modulo kernel T. So V modulo kernel T is also a vector space, right, isomorphic to image of T, right? Yeah, so take a dimension, right? So yeah, take a dimension, so you get the dimension V divided by dimension kernel equal to dimension image T. Yeah, so so quotient in the vector space just the abstract subtraction, right? So yeah, so this is yeah, but this use the group theory, right? So if you don't know group theory, then this proof will not work. Okay, so okay, so so I'm in the final page. Okay, so now let's go to a proof. Okay, so the proof is standard linear algebra. So let's standard linear algebra. So we have this, right? So let's see. So let's take the kernel, right? I know the kernel is a vector space, right? So I can take the basis. So I take the basis. The basis that I pick out to be, let's say, alpha 1, alpha 2. Okay, so let's say the dimension of kernel is dimension of kernel T to be, let's see, to be alpha. Sorry, to be, let's see, to be X. Okay, so the notation, right? So alpha 1, alpha X be a basis. Be a basis of kernel T. So basis means that the kernel T is spanned by alpha 1 to alpha X, and they are all linear independent, right? And so this is definition. And the second that so the second step is I create. So I can create rest, right? Because I know that the dimension V, let's denote dimension V to be n. So I can create another n minus x basis to be a basis of V. So I create, so I can say that alpha 1, alpha 2, alpha x, and beta 1, beta 2, beta 3, up to beta n minus x. Oh, why did I do this? Sorry. Beta n minus x will be, let's see, will be a basis of V, right? So I take this to be a basis of V. Okay. Okay, so I know that V is spanned by this. So that's talking about the image of T, right? So image of T will be just a span of T alpha 1, T alpha 2, up to T alpha x, and the T beta 1, T beta 2, up to T beta n minus x. Okay, so, but all these are 0, right? So we don't care. So image T is a span of T beta 1, T beta 2, and the T beta n minus x. Okay, so there are total we have n minus x of limit, right? So the rest, so the rest is just to show, so I already proved that the image T is spanned by this vector, right? So in order to prove the dimension of image T, is called, in order to prove the dimension image T just n minus x, we just need to show that they are linear independent. So linear independent. This is very hard to write. Yeah, but I mean, okay. Yeah, so you just need to prove that they are linear independent. Then once you prove that they are linear independent, then total n minus x, you get this, right? And then you already assume that the dimension of kernel T is x. So sum of them will give you the dimension image T plus dimension of kernel T will give you a. Okay. Right? Okay. So we need to show that they are linear independent. Oh, so by definition, if not, so let's say we have C1, C2, right? So we get summation of Ci T beta I from 1 to n minus x, which is 0. So we get the T summation Ci beta I. So this is the linearity, right? 0. Okay, so but from here that you know that I from 1 to n minus x Ci beta I belongs to what? Belongs to kernel of T, right? Which is contradiction. The reason is that my assumption is that all of it should be basis of V, right? And the basis is n. So we have dimension of, so that means all of them should be linear independent by my contradiction, my construction. Right? They should all be linear independent. But now I get a contradiction says that the rest, there are some linear combination will be kernel of T, so which is a contradiction. But unless all Ci's are zeros. Also, which prove they are all linear independent. Since they are linear independent in total, they have n minus x. So I prove that the dimension of image T is n minus x. Also, which prove the theorem. Okay, so that's final, just simple remark. So notation is that people like to define rank of T, which is rank is another good word. I mean, hard to think intuitively, but actually it's just dimension of T, and the nullity of T is just the dimension of kernel T. Okay, so the theorem is just the dimension of V is the same as dimension of image T and the dimension of kernel T. Okay, this theorem is a famous result that I think is maybe the first one, the most important theorem in linear algebra. Okay, so see you guys next videos.